Okay, so now we're going to start chapter 6, which looks at bones and bone structure. So we were introduced to bone tissue in chapter 4, but now we're going to get into a lot more detail. So the first section are the functions of the skeletal system. You had this in chapter 1, so this should be a review. So the skeletal system has several major functions. The first one is to provide support. So the skeleton actually serves as a framework for the attachment of a lot of other tissues and organs. So it's sort of like, think of like the coat rack that you hang your coats on. So the skeleton is like the main support source for the body, and we sort of build the body around it. The skeleton also serves to store minerals and lipids. So calcium is the most abundant mineral in the human body, and calcium is stored in the skeleton in your bones. Also phosphorus in the form of phosphate groups, and then there's some other trace minerals that are also stored in the bones. Plus, you have yellow bone marrow inside your bones, and this is a place where you can find adipose tissue, which provides a place to store lipids. The skeleton also serves as the place where new blood cells are produced, and this occurs in the area of the bone called the red bone marrow. And you'll get into more detail about blood cell production in 2252 when you get into the cardiovascular system chapters. But for now, we're just going to let you know that blood cells are produced inside bones in the red bone marrow. The skeleton also acts for protection. So it protects the soft organs and tissues of the body. So for example, your brain is protected inside your skull. Your heart and lungs are protected inside your rib cage. Some of your lower abdominal pelvic organs are protected inside of your pelvis, etc. And then finally, the skeleton serves as leverage. And so muscles will pull on bones. Muscles actually use bones like levers, and this allows you to produce movement and to exert force on objects in your environment. In this section, we're going to talk about how we can classify bones based on their shapes, their markings, and their structure. So everyone has at least 206 bones, well, unless they've had an amputation. But some people may have more depending on the number of sutural and sesamoid bones that they have. And we'll talk about those two types of bones in a moment. You will need to know the names of almost all of these 206 bones in the upcoming chapters. It's not as scary as it sounds because like 56 of those bones are called phalanges, for example. But you are going to need to know all of the bones by the time we get done with this unit. So you can classify bones by shape, markings, and structure. And let's look first at the 6 different types of shapes that are possible. So one of the types of shapes is called a sutural bone. And these are small, flat, irregular shaped bones. They can be very small or up to about the size of a quarter. They vary highly from individual to individual. Some individuals may have none. Some individuals may have multiple ones. And again, they range in size from very small to about the size of a quarter, and they're located within the sutures of the skull. So when we talk about the structure of the skull in chapter 7, you're going to learn that sutures are the joints between one skull bone and another skull bone. And so these sutural bones can form within these joints. So some people might not have any, some people might have one, some people might have more than one. Here's an example of a real skull where the person has like, it looks like 3 sutural bones on this side and another 3 sutural bones on this side. So again, these are highly variable from individual to individual, but if a bone forms in this suture or joint between 2 of your cranial bones, we call that a sutural bone. You can also classify bones by calling them irregular bones. These are bones that have complex shapes. They can be short, flat, notched, or have ridged surfaces. And some examples of these are like the vertebrae in your spine. Also, your bones that make up your pelvis, like your ilium, your ischium, and your pubis. And then several of your skull bones, and especially the facial bones, are also considered to be irregular. The next shape is a short bone. So as the name suggests, these are small and boxy, so they look kind of short. And you can find these types of bones in your wrist and your ankle. So carpals are the bones in your wrist. Tarsals are the bones in your ankle. The next shape is a flat bone. So flat bones have thin parallel surfaces, right? So if we take a cross section like shown over here on the right, you can see the thin parallel surfaces with spongy bone in between. These provide protection for underlying tissues, like for example, a lot of the bones on the roof of your skull, like your parietal bone, frontal bone, and occipital bone, are flat bones and they protect your brain. They also have a large surface area for the attachment of muscles, and you can find these, for example, like I just mentioned, the cranial roof of your skull, also your sternum, which is your breastbone, your ribs, and your scapula, which is your shoulder blade. The next shape is a long bone. These bones are long and slender, and they usually have, the ends are usually swollen up a bit compared to the middle. And you can find long bones in your appendages. So you would find these in your arms, both upper arm and lower arm, your legs, upper leg and lower leg, in both your hands and your feet, so like the sole and the palm, and your digits, so your fingers and your toes. So when you think of the appendicular skeleton, which we're going to cover in chapter 8, the appendicular skeleton has a lot of long bones in it. And the last classification by shape is a sesamoid bone. These are small, round, flat bones that are shaped somewhat like a sesame seed. They actually develop inside tendons, and remember, tendons are structures that connect muscles to bones. Everyone has at least one sesamoid bone called the patella. You might have, before you took A&P, you might have called this your kneecap, but now you're going to call it your patella. Everyone has this one. Other people may have more or less sesame bones in other areas of their body. There are actually 26 different locations, so 26 tendons where these bones can develop. And again, this is highly variable from person to person, except everyone has a patella. And interesting little fact, so the patella, which again is a sesamoid bone that everyone has, forms inside of the tendon of a group of muscles called the quadriceps femoris. You might have abbreviated this muscle as your quads before, and later when we get to chapter 11, we're going to learn the 4 muscles that make up the quadriceps femoris. So quad means 4, so this is a group of 4 muscles. But at the inferior tendon, so the tendon at the bottom of this group of muscles, is where the patella forms. So the patella actually forms inside that tendon, and as I mentioned before, prior to taking A&P, you probably called this your kneecap. So this is an introduction to bone markings. So I won't test you specifically over bone markings, but I will tell you that when you get to chapters 7 and 8, you're going to have to learn all of the bones of the body, as well as a lot of the markings found on several of the bones. So go ahead and get familiar with this terminology, and especially as you get into chapters 7 and 8, come back here and refresh your memory as to what these different markings are called, because again, trying to connect new information to older information is easier than trying to remember a bunch of facts that aren't connected in your mind. So in general, projections are found on bones where tendons or ligaments attach, or where an adjacent bone forms a joint. So for example, you might see parts of bones called processes or a ramus. Places where tendons or ligaments attach might be called a trochanter, a crest, a spine, a line, a tubercle, or a tuberosity. Places where one bone might form a joint with another bone might be called a head, neck, facet, condyle, or trochlea. And then openings are found where blood vessels or nerves pass through bones, and you're going to see openings called things like sinuses, a foramen, fissure, meatus, or canal. And then depressions are found where blood vessels or nerves lie alongside a bone, and you'll see these called things like a sulcus or a fossa. So again, get familiar with this terminology. You're going to see a lot of this over and over again in chapters 7 and 8. And the last little part of this section is the bone structure of a long bone versus a flat bone. So if we look at a long bone, all long bones have 3 main areas. The first area is the diaphysis, and this is the extended shaft. So this is the long, skinny part of the bone. The walls of the diaphysis are made of compact bone, and we're going to talk about the different types of bone coming up here shortly. Sometimes this is also called the cortex of the bone. In the inner space, there's actually a cavity inside long bones, and this is called the medullary cavity. Some sources might call it the marrow cavity. You should go ahead and get used to calling it the medullary cavity. And just a little quick aside here, you're going to see this over and over again in A&P, so go ahead and get this in your brain. When you see the word cortex, it's referring to something on the outside or to the outermost position. And when you see a word related to medulla, like medullary, that means innermost, so the very inside of something. So in this case, the compact bone is forming the cortex or the outside of the diaphysis, and on the very deep inside you have the medullary cavity. And this is where you actually will find some bone marrow, which we'll cover a little bit later. The very ends of the bone, so you have an end on both sides. This is the epiphysis. This is the expanded areas at the ends. This is composed of mostly spongy bone. So on the inside, it's all spongy bone, and you can have bone marrow here as well. And then there is a very thin layer of compact bone on the outside, again called the cortex. And then the metaphysis is like the neck. So the metaphysis joins the epiphysis to the diaphysis. So it's the narrow region. So think of it as like a neck between the rounded ends of the epiphysis and the diaphysis shaft in the middle. And then contrast that to a flat bone structure. So with flat bones, think of them as like a spongy bone sandwich. So you have a thin layer of compact bone, again, forming a cortex, because that's what we call an outermost layer. So a thin layer of compact bone on both sides, so that's like the bread of your sandwich. And then on the inside, you have spongy bone. And again, we're going to talk about the different types of bone coming up here shortly. And the spongy bone, when it's found inside of the cranial bones, it has a special name. We call it diploe. So otherwise, you can just call it spongy bone. In this section, we're going to look at bone tissue, including the matrix and the multiple cell types that you can find in bone tissue. So some of this should be a review from Chapter 4. In Chapter 4, we gave you a brief overview of bone histology. Remember that bone is a type of supporting connective tissue. Cartilage is the other type of supporting connective tissue. And if you remember from Chapter 4, we talked about the matrix of bone. Remember, all connective tissue has a matrix, and a matrix is composed of a ground substance and protein fibers. And in bone, there is very little liquid ground substance. Instead, you have a dense matrix made up of a lot of collagen fibers and deposits of hard calcium salts around that collagen. You also find osteocytes, which are bone cells located inside these little pockets called lacunae, and we looked at that on some images of tissues. We also saw that we have these little canaliculi that extend between one lacunae and another, and between the lacunae and the blood vessels that are in the middle central canal. And we also talked about how the outside of a bone is covered by a periosteum. So that is a membrane made of dense irregular connective tissue. So now we're going to go into a little bit more detail than we did in Chapter 4. So we mentioned that the matrix is made up of the collagen fibers and the calcium salts. So to get more specific, 2/3 of the weight of bone is made up of a calcium salt called calcium phosphate. Calcium phosphate by itself forms very hard crystals, but the crystals are inflexible and brittle and can break easy. However, they're good at resisting compression. So they can withstand a lot of weight put on them, just not like lateral forces. Calcium phosphate reacts with calcium hydroxide in the body to form hydroxyapatite crystals. And these crystals, as they form, they can incorporate other calcium salts like calcium carbonate and even other minerals like magnesium and fluoride. The other 1/3 of the weight of bone are the collagen fibers. And these fibers are very strong and they are very flexible, but they have little resistance to compression. If you have just a collagen fiber and you try to compress it, it'll just bend. So together, if we take the calcium phosphate, which is inflexible but good at resisting compression, and we mix that with the collagen, which is strong and flexible but has little resistance to compression, we get the bone matrix. So putting these two substances together makes a very strong, somewhat flexible matrix that's highly resistant to shattering when compressed. And you can compare the matrix of bone to like steel reinforced concrete. So with steel reinforced concrete, you get something that is stronger than the steel by itself or the concrete by itself. When you pour the concrete around the steel rods, the whole overall final product is very, very strong. And bone matrix works the same way. The collagen serves like the steel fibers, and the calcium phosphate is like the concrete that you pour around it. And with both of them together, you have a very strong final product. So remember that bone matrix is 2/3 calcium phosphate, 1/3 collagen, and the collagen and the calcium phosphate together make up the bone matrix. And the matrix is going to be the same whether it's going to be compact bone or spongy bone. And we're going to look at the difference of these two types of bones in a later section. Cells actually only account for 2% of the mass of bone. So bone is primarily this matrix of collagen and calcium phosphate with a very small number of cells. However, the cells are important, and we're going to look at those next. So there are 4 types of bone cells. The first type we've already introduced you to. These are called osteocytes. Remember, osteo means bone, cyte means cell. These are your mature bone cells, and you have more of these than any of the other types of bone cells. So they're your largest bone cell population. And here is an image again of an osteocyte. It's the little cell in the middle you can see his nucleus. And he has extensions of cytoplasm that extend outward into these little channels called canaliculi. And the matrix is going to be those collagen fibers and calcium phosphate that's going to be sandwiched in between all of these little canaliculi. So the osteocytes are located in these lacunae. So there's 1 osteocyte per lacuna. Osteocytes cannot divide, so when bone needs to repair itself or grow, other cells are involved. And the canaliculi connect one osteocyte to another osteocyte, and they also connect them to the blood vessels that are found in the middle of the osteons. And so here is an image at the bottom that can help you better see how this works. So each of these little spaces are the lacunae. Each space or lacuna has a single osteocyte, and the osteocytes send out these little cytoplasmic extensions into these canaliculi, which are these channels between one lacuna and another. And when one osteocyte actually touches the cytoplasm of another osteocyte, they have gap junctions there. And if you remember from chapter 4, gap junctions allow the cells to share ions and other small substances, so it allows for very rapid communication. Here's another image, again, to help you visualize this, where we can see an osteocyte in a single lacuna. We can see how he extends the cytoplasm out through the canaliculi and meets up with the cytoplasm extension of another osteocyte, so they communicate here with gap junctions. They can also extend their cytoplasm through the canaliculi to the inside of the bone where the blood vessels are located, and that's how they can get nutrients and release waste. So osteocytes function to maintain the protein and the mineral content of the matrix. So they are essentially surrounded by matrix. So all of this around them is the bone matrix. That's the collagen and the calcium phosphate. So they can maintain it. They can break it down a little bit and rebuild it. So they help to keep the bone strong and functioning properly by constantly updating and making subtle changes and monitoring the strength of the bone around them. Also, if a bone is damaged, the osteocytes can revert back to other cell types, so they can become cells called osteoblasts or osteogenic cells, which will then help to repair the damaged bone. And we're going to look at those cell types next. So the next type of cell is an osteoblast. These produce new bone matrix. So when you see the root word blast, think of that as a cell that is like making something. So it's like a new cell making something new. So an osteoblast makes new bone matrix. The process of making new bone is called osteogenesis, and you may also see it referred to as ossification. And so the osteoblasts are usually going to be located around the outer edges of the bone. Because as they make the bone in the inside here, that's where you're going to get your osteocytes. So osteoblasts are on the outside making new bone. So this is what they do. They make and release components of the matrix. So first they're going to release the protein fibers, so the collagen fibers. So this is like putting down the steel rods of the steel reinforced concrete. And when you just have all of the protein fibers in place, we call that osteoid. So that's like pre-bone. So that's where we've got protein fibers, but we haven't added those calcium salts to it yet. So it's not quite fully bone. And then once we have the osteoid, the osteoblasts then trigger the deposition of calcium salts. And once you get those hydroxyapatite crystals made from calcium phosphate, the osteoid is now considered to be real bone. And as this happens, as the osteoblasts are making new bone, they actually get themselves stuck in the new bone they're making. So they get surrounded by the osteoid, and then they get surrounded by the mineral composition, so the calcium salts. And then once they're completely embedded, they're now become an osteocyte, and they're just going to hang out there for the rest of their lives and maintain and take care of that bone around them. So osteoblasts will turn into osteocytes as they are building new bone. So think of it as kind of like a painter that paints himself into a corner and then he's stuck there. So the osteoblasts are making new bone, and as they surround themselves with new bone, they get stuck in the new bone, and then they become osteocytes, and now their job is just to maintain that area of the bone. So osteogenic cells, which can also be called osteoprogenitor cells, these are your mesenchymal cells or your stem cells. Right, so these are the ones that can basically start off the whole process by becoming osteoblasts. So you have the fewest number of these hanging around because you really only need these in cases of where your bone is like injured or broken. Otherwise, they just chill and do nothing. All right, so you have your osteoprogenitor cells, which differentiate into your osteoblasts. They are located in the inner layer of the periosteum and the endosteum. So we already talked about the periosteum, which is the covering around the outside of the bone. You probably can guess by knowing your root words that endosteum would be the covering on the inside of the bone. So on the inside part of the bone where you've got that medullary cavity, you have a covering of endosteum. And in both of these coverings, the periosteum and the endosteum, this is where you'll find your osteogenic cells, and they get activated once there is damage, and then when they sense the damage, they become osteoblasts, which can then start making new bone. So they function to produce new osteoblasts when needed. So these are very important in the repair of a break or a fracture to a bone. And your last type of bone cell is an osteoclast. These are cells that remove and recycle bone matrix. So osteoclasts are the ones that break down bone. These are actually very giant cells. They can have 50 or more nuclei. They are actually derived from stem cells that produce white blood cells. So they are more closely related to your white blood cells than they are to the other types of bone cells. They function to secrete acid and proteolytic enzymes that dissolve the matrix. So it's going to break down the collagen fibers, and it's going to break down the calcium phosphate salts. We call this process osteolysis, again using your root words. Lysis means to break down. Another term that is often used is resorption. And why would we want to break down our bone? Well, you're going to find out a little later in this chapter that our bone is constantly being broken down and rebuilt. So our bones are kept in very tip-top shape throughout our lives. And this process is also useful if we need to release minerals that are stored inside the matrix of bone. So remember, one of the functions of bone is to store minerals. So if we need extra calcium, or we need extra phosphate, or we need even extra magnesium, or any type of mineral that's stored in the bone, we can't get to that mineral unless we break the bone down. So osteoclasts break the bone down, and in doing so, it helps with the process of remodeling the bone, and it helps to release minerals that are stored in the matrix. Note, this will take you back to chapter 3. Osteoclasts have a ruffled border made of microvilli, and that helps them increase the surface area, which helps them in their process of breaking down the bone matrix. So a quick review of the different bone cells. So this is a picture of an osteon. We'll talk about the structure of an osteon in a moment, but just pay attention that we have our osteocytes in these little pockets called lacunae. They are connected to each other through these little channels called canaliculi. Around the outside is where we would find our osteoblast, and you would also find your osteoclast around the outside as well. And these three, osteogenic cells, osteoblasts, and osteocytes, these three cells are all related. So your osteogenic cells can become osteoblasts, your osteoblasts can become osteocytes, and your osteocytes can go back to being osteogenic cells, or they can go back to being osteoblasts. So these three are very related, but remember that your osteogenic cells are your stem cells, your osteoblasts make new bone, and your osteocytes maintain your bone. And then you have the separate osteoclast, which breaks down or dissolves bone, and this cell is completely unrelated to the other three. It's actually more closely related to macrophages, which is a type of white blood cell. Here is a quick little video I found that will show you the different cell types again, and the images can also help you remember what these different types of cells do.
Bone is a dynamic tissue that is continually being built, broken down, and rebuilt in a process called bone remodeling. Bone tissue is broken down and resorbed by multinucleated cells known as osteoclasts. These cells are derived from monocytes which originate within bone marrow. Osteoclasts play an important role in liberating minerals and other molecules stored within the bone matrix. Bone tissue serves as a repository for vital minerals, including calcium phosphate and various biologically active molecules, such as growth factors. The release of calcium from the bone can play a role in maintaining its homeostasis within the body. The cells responsible for building new bone tissue are known as osteoblasts. Osteoblasts are thought to be derived from cells found to be associated with blood vessels. Once active, they start to produce the organic component of bone, osteoid, which is predominantly made of collagen. Minerals start to crystallize around the collagen scaffold to form hydroxyapatite, the major inorganic constituent of bone, which contains calcium phosphate. Bone mineral density, or BMD, can be used to estimate the strength of bone and to assess the risk of fracture. As osteoblasts form new bone tissue, many become embedded within the matrix and differentiate into osteocytes. The structure, composition, and cellular processes that occur within bone allow it to simultaneously serve as a calcium reservoir, while providing structural support for the vital organs and for locomotion.
In this section, we're going to look more closely at bone structure, specifically the difference in structure between compact bone and spongy bone, and then we'll talk about the two bone membranes. So first, let's look at compact bone. Notice that compact bone can also be referred to as cortical bone. So some textbooks and medical sites will say cortical bone instead of compact bone. They are the same thing. And with the compact or cortical bone, the basic functional unit is called an osteon. And an osteon are these little circular structures that we looked at back when we were looking at the histology of bone tissue, right? And these are the basic functional units of bone. So the osteocytes in a osteon are in concentric little circular layers called lamellae around a central canal. And the central canal is where you would find the blood vessels. Notice that in older textbooks, the central canal is being called the Haversian canal. But as I mentioned in chapter 1, we're trying to get away from things that are named after people, so we're calling this the central canal now. But you have a central canal in the middle of each osteon. So the central canals run parallel to the surface of the bone, so they're like little columns inside the bone. And then you have perforating canals, which are perpendicular little channels that connect each central canal to another central canal and also to the blood vessels on the outside of the bone. So remember, one of the characteristics of bone is that it has an extensive blood supply, so you've got these blood vessels running all throughout the structure of bone. The collagen fibers within the lamellae or layers actually form spirals. So if you were to pull out some of the concentric circles or lamellae and stack them up on top of each other, like in this bottom right picture, you'd see that the collagen fibers actually form these spirals, which help give bone even more strength and resistance to compression. So if we look in between the osteons, so again, the osteons are the circles. If you look in between them, you will notice there are some flattened areas of matrix, and these are called interstitial lamellae. And these are actually remains of old circular osteon. So old broken down osteons. So you have an osteon, and remember I mentioned before that bone is always undergoing remodeling. So the osteons are getting broken down by osteoclast and built up again by osteoblasts. And so when the osteoclasts have almost completely broken down an osteon, you'll see these little remnants squeezed in between the other osteons, and those are called interstitial lamellae. Around the outside of the bone and lining the inside of the bone, you have circumferential lamellae. So these are going to be an entire circle of osteocytes and matrix that surround the entirety of the outside of the bone and then surround the inside of the bone. So you find this only on the outer and inner surfaces. And this is where you're going to have your two bone membranes. So on the very most outer surface of the outermost circumferential lamellae, you'll have your periosteum. And then on the innermost surface, around the concentric or the circumferential lamellae in here, you would have your endosteum. Note that you've also got some endosteum lining the central canals, but we'll talk more about the endosteum in a moment. So here's a quick review. So an osteon again, so up here on the left is a cartoonish version of an osteon to make it a little bit more simpler and easy to see. So you've got your central canal in the very middle with your blood vessels and nerves. You've got your lamellae, which are these layers surrounding it. So these would be concentric lamellae and circular layers. This is where you find your osteocytes and the lacunae with the little canaliculi reaching in to touch another osteocyte. And then around the outside is where you would have the outermost area of the osteon. This is where you would find your osteoblast and your osteoclast, who are going to play a role in the remodeling. And the picture to the right here gives you an idea, again, of those lamellae. This pulls up and shows you some of the circumferential lamellae. So these are the layers on the outside of the compact bone. And you can also see, again, that the outermost layer is part of the periosteum. And notice before we go to the slide that actually talks more in depth about the membranes, notice how the fibers of the periosteum are connected to the fibers in the bone itself. So we're going to talk about that in a bit, but notice that in this picture. So spongy bone structure. Also notice that spongy bone can be referred to as trabecular bone. So again, certain textbooks or sources might use the word trabecular bone, but it's the same thing as spongy bone. Now, spongy bone is made up of a meshwork of bone matrix. We do not have osteons in this case, so none of the little regular columns. It's just the bone matrix is kind of going in a bunch of different directions, and that meshwork is called trabeculae. So that's why this is sometimes called trabecular bone. So it looks like a branchwork of little struts going in a whole bunch of different directions. So the trabeculae are very branched, and within a single bone, they tend to be oriented along the stress lines. So the trabeculae in the spongy bone will orient themselves according to how the bone takes stress or force. There are no capillaries or venules on the inside of the trabeculae, like you have the central canal in the middle of osteons and compact bone. You don't have that with spongy bone. Instead, the osteocytes are getting their nutrients from the surrounding bone marrow. So you typically find spongy bone structure where you have bone marrow. And you'll see that there are little holes on the outside of the struts of trabeculae. Those are the canaliculi of the osteocytes that are opening up, and then that way they can get the nutrients and get rid of their waste with the surrounding marrow around them. So the spongy bone structure makes it much lighter than compact bone. So your body will use spongy bone in areas where there's not a lot of stresses on the bones, and this will help to reduce the overall weight of the skeleton, which makes movement easier. And the spongy bone, as I mentioned before, surrounds bone marrow, so it also supports and protects the cells of the bone marrow. So if we compare the compact bone versus the spongy bone, again, compact bone is going to be found in, it's going to be thickest where the stresses occur in a limited number of directions. So if we look at the femur, over here on the right, the femur is your upper leg bone. You're going to have a compact bone. It's going to be very thick around the outside of the femur, the cortex of the femur, and that's going to allow the femur to withstand compression and tension that runs along the long axis of the bone. So basically, like if the bone is a column, it can withstand forces because of the compact bone that are coming like down, right, from top to bottom. So compact bone is very strong along the axis of alignment of those osteons, because think of those osteons as, you know, millions of little tiny columns in there. So to give you an example, the femur can withstand 10 to 15 times your body weight along the long axis. So again, if you put the weight up here and the weight comes down, the femur can withstand it. What will typically cause a bone like the femur to break is if you exert a very strong force from the side, like in a car accident, like a person getting hit by a car. Now the force is coming, it's not coming perpendicular or parallel to the long axis of the bone, it's coming perpendicular to it. So it hits it from the side, and that can snap a bone like this. Spongy bone is found where bones are not heavily stressed or where the stresses are multi-directional. So the stresses come from different angles, like right up here at the very top of the femur, where the body weight is transferred to the long axis of the bone, you'll find spongy bone. So the trabeculae within the spongy bone is often oriented along stress lines, so think of them as like cross braces to help give extra support in those areas. So before we go on, I have a video to let you visualize the differences between compact and spongy bone. Remember the alternate terms of cortical and trabecular bone.
The human skeleton gives the body its shape and provides physical support for the systems contained within. It also forms part of the musculoskeletal system that enables us to move. The structure of bone is optimized so that it is strong but relatively lightweight. The interior of bone is composed of bone marrow. It is surrounded by two major types of bone tissue: cortical bone, or the hard outer shell of bone, and trabecular bone, the spongy-looking center. The amount of each type of tissue in bone is dependent on the function of that bone. The basic unit of cortical or compact bone is the osteon. It is composed of successive concentric lamellae. This structure contributes to bone strength by resisting bending. Cells called osteocytes are distributed within the concentric lamellae. Osteocytes form a complex network that is thought to be important in maintaining the viability and structural integrity of bone. At the center of the osteon is the Haversian canal. These canals contain blood vessels and nerves. The blood vessels within bone facilitate the exchange between osteocytes and the blood. Trabecular bone is present in the interior of some bones and resists compression. Osteocytes are also contained within its structure and again play an important role in sensing local changes in strength. Trabeculae are covered in a layer of flattened lining cells.
That's the endosteum.
In the dynamic process by which bone is formed and broken down.
Endosteum.
Bone marrow is found within the interior of bones.
So we left off in that video with her talking about the bone marrow inside bones. So there are two types of bone marrow. There is red bone marrow, and this is where new blood cells are formed. And you can find the red bone marrow in the epiphyses of the long bones. Remember, the epiphyses are the enlarged ends of the bone. And for example, this picture here shows the femur, and so the epiphyses would be the two ends, and that's where you can find red bone marrow. You can also find it in the inside of other flat bones, like the sternum or the ilium, which is part of your pelvis. And in that case, remember we talked about the spongy bone sandwich that flat bones make up. So you have cortical bone on the outside, spongy bone on the inside. Those bones will also have red bone marrow. Now, your long bones can also have yellow bone marrow, which is where you store adipose tissue. And so this would be found in the medullary cavity of the long bones, like the femur, right? So that's the yellow marrow. It's going to be energy storage and adipose tissue. Red bone marrow, which is your epiphyses, and inside your flat bones is where you're going to make new blood vessels. And this is just a picture of a cross section of bone where you can see the hard cortical bone or compact bone on the outside. You can see the spongy bone on the inside, and then you can see the difference between the red bone marrow and the yellow bone marrow. And the final part of this section are the two membranes, the endosteum and the periosteum. So both of these membranes have a fibrous outer layer and a cellular inner layer. And the periosteum is going to be the outermost covering of bone. It functions to isolate bone from the surrounding tissue. It also provides a route for the circulatory and nervous supply to the bone, so you can find the blood vessels and nerves embedded in it. And it participates in the bone growth and repair because as part of its cellular lining, you will find the osteogenic cells. And remember, they're the ones that can change into osteoblast when the bone is damaged or broken. As I showed you in that previous picture a couple slides ago, the fibers, the collagen fibers of the periosteum are interwoven with the circumferential lamellae. So you have collagen fibers in the periosteum that are actually cemented into the bone itself, into the circumferential lamellae. And then when you have tendons and ligaments attached, the tendon and ligament fibers are also cemented into the membrane and to the bone itself. We call these perforating fibers. And the take-home message is that the membrane of the bone, along with the tendons and ligaments that attach to bones, are all very tightly held together. So in some cases, like if you have a really strong pull along a tendon, rather than tearing the tendon away from the bone, it can actually break the bone. So the tendon and the periosteum and the bone itself are all very tightly interwoven with these collagen fibers, making them very, very strong connections. The endosteum is the inner covering of the bone, so you find this around the spongy bone area inside of bones, and you can also find it inside the central canals. So the endosteum becomes active during bone growth, repair, and remodeling because this is where you're going to find your osteoclast, your osteoblast, and your osteogenic cells. So as I mentioned, it covers the trabeculae and the spongy bone. It also lines the central canals of the osteons in the compact bone. And it's an incomplete cellular layer made up of the osteogenic cells, the osteoblast, and the osteoclasts. In this next section, we're going to look at the first type of bone growth. There are two types of bone growth, but I broke them into separate sections so it wouldn't get too long. So this first type we're going to look at is called endochondral ossification, and we'll also talk about the differences between interstitial growth and appositional growth. So the bony skeleton, or the bones, actually begin to form when the embryo is about 6 weeks old, so 6 weeks after fertilization. The embryo is only a ½ inch long at this stage. And before this stage, all of the bones were made completely of cartilage, so we say they were cartilaginous. So bone growth starts 6 weeks after fertilization, and it will continue well into adolescence, and there are some bones that don't stop growing until approximately age 25. So some terminology to go over before we look at the steps. So the term calcification is a term we use when we talk about depositing calcium salts like the calcium phosphate. This does happen to make bone and bone tissue, but this term calcification can also apply to processes that happen in other tissues. These are usually pathological processes. For example, your arteries, you might have heard the phrase hardened arteries. So your arteries can calcify. That is when you get calcium salts deposited into the walls of the arteries and it makes them stiff and inflexible. So calcification does happen in the skeleton, but keep in mind that it can happen in other tissues as well. The term ossification is a term that we specifically use when we're talking about bone formation. There are two types of ossification or bone growth. The first one is called endochondral ossification, and we're going to talk about this one first. This is when you have an already existing cartilage model and the bone replaces the cartilage. So look at your root words. Endochondral actually literally means within the cartilage. So this is bone formation that takes place within a already existing cartilage model. So with endochondral ossification, bone can grow in two directions. Interstitial growth is when the bone increases in its length, so the bone gets longer. And appositional growth is when it increases in its width, so it gets thicker and wider. The other type of bone growth we're going to talk about in the next section is called intramembranous ossification, and this is when bones develop from an embryonic connective tissue called mesenchyme or a fibrous connective tissue. But first, we're going to look at endochondral ossification. So most bones start from hyaline cartilage. That's one of your three cartilage types. And the hyaline cartilage will initially form and look like a little mini model of the skeleton with all of the bones there, but they will be made of cartilage instead of bone. So to make those cartilage mini models into bones, we have to go through several steps. So the steps in endochondral ossification are at the beginning, the cartilage starts enlarging. So the chondrocytes, remember these are the cells that you find inside of cartilage. The chondrocytes will enlarge within the matrix, making like these little bubble-like structures. So the lacunae will get larger, the chondrocytes will get larger. Then because the lacunae and the chondrocytes are getting larger, the matrix, which is the fibers and fluid between them, the matrix gets pushed away and reduced to very thin struts. And then these thin struts are going to start to calcify. And remember, calcification is when you have the deposit of calcium salts around collagen fibers. Remember, hyaline cartilage already has the collagen fibers. It just doesn't yet have the calcium salts. So once the calcification process starts, the chondrocytes become isolated. They can't get nutrients and get rid of their waste. So they start dying, and then they start disintegrating, and this is going to leave behind cavities within this hyaline cartilage model. The next step is that blood vessels are going to come in and enter the perichondrium. Remember that cartilage was avascular, so there was no blood vessels while it was cartilage. Also remember that the membrane on the outside of cartilage is called the perichondrium. So blood vessels are coming in, they're invading the perichondrium. They're causing the cells in the perichondrium to differentiate or turn into osteoblasts. And remember, osteoblasts are going to make bone. So the osteoblasts are now going to form this thin layer of bone around the shaft of the cartilage. Remember, this middle part's called the diaphysis or the shaft. And so this is going to form a very thin bone collar just around the middle part or the diaphysis. At this point, we call the membrane the periosteum because now we actually have bone. So now it's the membrane lining the bone, and it's called the periosteum. It's still the perichondrium out here where there's still cartilage, but around the bone collar, it's the periosteum. So the next step is that the blood supply is going to continue to push into the cartilage, so it's going to migrate to the heart of the cartilage. There are fibroblasts that migrate along with the blood vessels, and these are going to differentiate into osteoblasts. And again, remember, osteoblasts make new bone. So the osteoblasts are going to start building spongy bone made out of those trabeculae that look like little struts. We call this the primary ossification center because it is the first part of this cartilage model that is getting turned into bone, right? So it's the primary or first ossification center. Bone growth at this point is going to continue to spread outwards to both ends, so top and bottom. And it will also spread out within the diaphysis as well. And so the goal here is to ossify the entire diaphysis. So step 4, now we pretty much have bone in the entire diaphysis region or shaft region. Osteoclasts are now going to be activated. Remember, osteoclasts break down bone, so they're going to start eroding or breaking down the trabeculae, and that's going to form a cavity, and that's how we get the medullary cavity formed in the very middle. So we're going to be left with compact bone on the very outside where the collar was, spongy bone lining the inside of the cavity, and then we're going to have the cavity itself. So at this point, we have a well-formed diaphysis, right, or a bone shaft. Bone growth is going to continue by increasing in length out to the sides, so top and bottom in this picture, and we're going to look at that in the next step. But you can also increase bone growth by increasing the diameter or making the bone wider. So we're going to look at that for just a second. So appositional growth, it occurs at the outer layer of the bone, so this very thin outer layer here that we called it a bone collar, and it's going to move outward, so it's going to make the bone wider, right? So you see my little arrows? We're going to go this way. That is appositional growth, and that makes the bone thicker or wider. So here is a better image to kind of visualize how this works. So again, appositional growth is an increase in width. So what happens is the cells of the periosteum on the outside become osteoblasts. They start depositing more bone, and so they're going to build up these circumferential lamellae on the outside of the bone. That's going to make the bone get wider and wider. It's going to increase the diameter, and then as the bone gets wider and wider, the osteoclast on the inside are going to keep eating away at the bone on the inside, and they're also going to enlarge the cavity to match the enlarged outer surface. So that is appositional growth, and that is where a bone increases in width. Now, back to our steps. Now, step 5, remember our diaphysis is done. We still have to ossify the epiphyses, which are the ends of the bone. So in step 5, the center of the epiphyses are going to begin to calcify. And that happens because capillaries and osteoblasts, so more blood vessels and osteoblasts, are going to come into the epiphyses, and they're going to start creating bone. And we're going to call these the secondary ossification centers, because this happens later than that initial primary ossification center in the shaft or diaphysis. So these are secondary ossification centers. The timing can vary from bone to bone, so these may start earlier or later depending on the bone, and also from one individual to another. And then step 6, so the epiphyses, those osteoblasts are going to work making bone, so now our epiphyses are going to get filled up with spongy bone. The cap of the original cartilage, right? So remember, this all used to be cartilage. So the outer part of the cartilage gets squeezed up, and that's going to become what we call our articular cartilage, which is the cartilage that covers the ends of bones at joints. So that's not going to go away. At this point, though, we also have this thin layer of cartilage at the metaphysis. So remember, the metaphysis is the region between the epiphysis and the diaphysis. So it's like that little neck region. Well, we still have some cartilage here, because if I go back to this picture here, remember, we started with a whole ball of cartilage. We're starting to ossify it from the inside out. So that's going to push some cartilage to the outside. That becomes the articular cartilage. But then there's also going to be this layer of cartilage at the metaphysis. This layer of cartilage at the metaphysis we call the epiphyseal cartilage. So that's what we give it that name once it gets squished down there. So the epiphyseal cartilage actually keeps growing. All right, so it has chondrocytes in it, and these chondrocytes continue to undergo mitosis, and they continue to divide. At the same time, you've got osteoblasts that are working to lay down new bone. Now, as long as the epiphyseal cartilage grows, the bone is going to increase in length. And basically think of it like a runner, right? So two runners that are running at the same speed. So the chondrocytes are making new cartilage while the osteocytes are making new bone. But if they're running at the same speed, then as you're making new bone, you're also making new cartilage. So this cartilage, this little piece of cartilage in between, is going to stay there. And I've got another picture for you in a second. So that's called interstitial growth, because that's going to increase the length of the bone. So basically, the chondrocytes are creating new cartilage at the same rate that the osteoblasts are making new bone. So this little piece of cartilage just sandwiched between the epiphysis and the diaphysis doesn't go away, right? And as long as it's still there, the bone can increase in length. So here's a picture that will hopefully help you see this a little bit better. So basically what's happening is we're getting new cartilage forming on one side of this plate. and then you've got new bone forming on the other. Then the cartilage is growing, the osteoblasts are replacing the older cartilage with bone, but you're making new cartilage, and the osteoblasts are still making the older cartilage into bone, but you're still making new cartilage. So as long as this happens, the bone is going to get longer and longer and longer, right? So it's like a race between these two, but as long as they're running at the same speed, the bone gets longer. Now, step 7, the final step, this only happens at puberty. So all of this right here with the interstitial growth, this only happens during childhood. So like while you're increasing in your height. So think about your leg bones are getting longer, your arm bones are getting longer, your finger bones are getting longer. This is happening throughout your childhood. Then at puberty, what happens is when you have you undergo puberty and you start getting those sex hormones, and those sex hormones are a signal to speed up bone growth. So at this time, the osteoblasts start working faster than the chondrocytes. So now the osteoblasts can actually overtake the chondrocytes. They can eventually replace all the cartilage because they start working faster than the chondrocytes can make new cartilage. So eventually, all of that cartilage is going to be turned into bone. And we call that epiphyseal closure. That is when you have the completion of the growth at this epiphyseal plate area. And you can see this on an x-ray. It looks like an epiphyseal line. You can see a faint line where that plate used to be, where that cartilage plate used to be. So once you're all done with bone growth, so this would be you're at your adult height, you're not going to get any taller, you're all done with your bone growth. The only cartilage that is left is this thin layer of hyaline cartilage on the end of the bone called the articular cartilage that's going to serve to reduce friction at synovial joints, which we'll talk about in Chapter 9. Here are a couple of pictures of x-rays to show you the epiphyseal cartilages. So if you look at a person who is still growing and you look at an x-ray, you can actually see a space at the epiphyses of their bones. That is where you have cartilage. So there is still cartilage there, which means that bone is still elongating or getting longer. Same here with the wrist bone, with the radius. And so you can see on the right side, this is an adult. So now this person their bones are no longer increasing in length. So now if you look very carefully, you can see the faint epiphyseal line where that cartilage plate used to be. So there's the one at the base of the thumb, and there's the one on the radius. And I like this picture from your textbook because it also shows, yay, look, a sesamoid bone. So remember earlier we talked about types of bones, and we said that some people can have more than one sesamoid bone. We all have the patella, but other people can have different numbers of sesamoid bones. This is an example of a sesamoid bone that's formed in the tendon at the base of the thumb here. I've got one more picture for you. I like this one a little bit better. So again, we can see the difference between what is called an epiphyseal growth plate on the left, and that's where you can actually see this little space here. That is the epiphyseal cartilage that indicates that this is the knee of a child who is still growing. And on the right side, you can see where the growth plate is gone, and now you only see the faint line. That's the epiphyseal line, and that indicates that this person is done growing. And of course, this doesn't happen overnight. This takes place over a series of years. So you can see this by x-ray as well. You can see where you have no fusion between the two. This is the epiphysis and this is the diaphysis. So in the beginning, there's no fusion. Then you can see some fusion. Then you see a little bit more. And then eventually it's completely calcified, and it can be even hard to see the line. So this can let doctors and x-ray technicians also estimate the age of a particular person using x-rays. In this section, we'll cover the other type of bone growth, which is intramembranous ossification. So this occurs when the osteoblasts differentiate within mesenchymal or fibrous connective tissue. And mesenchymal connective tissue is a type of embryonic connective tissue that's found during development. And so this does happen around the 8th week of embryonic development. So what sets this type of bone growth apart from the endochondral ossification is this one does not start with a cartilage model. So endochondral ossification starts with cartilage. Intramembranous ossification does not. It just starts in some connective tissue. This is also known as dermal ossification because it results in what's called dermal bones, because it's actually taking place in the embryonic dermal layer of the skin. And this is how you get the flat bones of your skull, like the parietal bone, the occipital bone, the frontal bone, your mandible, which is your lower jaw bone, and your clavicle, which are your collarbones. So here are the steps for intramembranous ossification. First, you have mesenchymal cells, which, remember, these are stem cells in connective tissue. They cluster and they start secreting osteoid, which is the collagen fibers that's going to become part of the bone matrix. And then around those collagen fibers, you get mineral deposits of the calcium phosphate salts, and then you result in bone matrix. So where these mesenchymal cells are differentiating into osteoblast, we call these little sections ossification centers. All right, so we have mesenchymal cells becoming osteoblast and secreting osteoid, which then is going to become bone matrix. And then these little ossification center areas, they grow outwards in small struts. So you get like one little section connects up with another little section, and you get a little strut or a small thin connection between them. And these are also called spicules. And then as this process continues, just like we saw before, the osteoblasts become trapped in the matrix that they're secreting, and then they become osteocytes. As the spicules continue to fuse, so now you've got all of these spicules are getting connected together in a much larger area. As this process continues and you've got blood vessels moving into the area, the blood vessels actually will get trapped in between these little struts of bone. So you get blood vessels trapped within the bone matrix. And then the next step is you're going to start noticing that it's going to look a lot like spongy bone. So you're going to have a large spongy bone center here with blood vessels weaving throughout. Then through the remodeling process, which we're going to go over in more detail, but that's basically breaking the bone down and rebuilding it, you get compact bone at the edges. And so remember, these are flat bones that we're making in this case, and flat bones are like spongy bone sandwiches. Remember, they have a layer of compact bone at the top and bottom, and there's spongy bone in between. So all of the bones that are made by this process are flat bones. So as this process continues, you'll get the compact bone on the outer edges. And then as the rate of growth decreases, so as the bone starts to reach its final size, the connective tissue around the bone will come together and organize into the periosteum, which is the bone covering. And that is intramembranous ossification. And in this section, we'll look at the blood and nerve supply to bone tissue. So if you remember from chapter 4, bone tissue is highly vascularized. That was one thing that set it apart from cartilage, which has no blood vessels. So we have lots of blood vessels in our bone tissue. And there are 3 major sets of vessels, and these are really separate from each other during the development process. But in an adult, these 3 sets of vessels end up being very interconnected, so it's hard to tell where one stops and one starts. But the 3 major sets that develop during the developmental process are the nutrient, artery, and vein, and there is one of each of these. And so they're going to come through the diaphysis, and there'll be a small hole in the diaphysis called the nutrient foramen. So whenever you see the term foramen, that means a hole. So the nutrient, artery, and vein come through this foramen and branch out into the diaphysis. The next set are the metaphyseal artery and vein. So there would be 2 sets of these because you've got 2 metaphyses. So one at each end. Remember, the metaphysis is the neck between the diaphysis and the epiphysis. So during development, the metaphyseal vessels are supplying blood to the epiphyseal cartilage, which in this picture, the cartilage is already gone and we have that epiphyseal line here. But you can see how these vessels were at the top and the bottom of where that cartilage used to be. And same thing down here. Here's your epiphyseal line, and you can see where the epiphyseal vessels ran along the top and bottom. So they supplied blood to the epiphyseal cartilage during development, and then in an adult bone where the growth has stopped, you'll see these vessels clumped around the epiphyseal line. And the final set of vessels are the periosteal vessels. And so these are going to be on the outside and associated with the periosteum. And they are supplying blood to superficial osteons. So that's osteons that are closer to the surface, right? So the nutrient artery, nutrient foramen, they go all on the inside, but the bone cells that are on the outside need blood too. So those are supplied by the periosteal arteries and veins. And like I said, after development has finished and the cartilage is gone, all of these blood vessels become very interconnected. So they really are only distinguishable as these three sets during development. Bone also has a very large sensory nerve supply. So everywhere you see blood vessels, you're also going to have nerves running through the bone. And this is why bone breaks can be very painful. Now we're going to talk about remodeling, which I've mentioned a couple times before. So your bone is continuously being broken down and built up again, and this process is called remodeling. So remodeling is a process of the continual recycling and renewing of bone. So this is an interplay between your osteoblast, your osteoclast, and your osteocytes. And normally the activities are balanced. So what you have going on shown in this little image down here, so here's normal bone at the top. So normally what you would have is the osteoclast will break down some of the bone. So remember, osteoclast break down bone. Then those osteoclasts are going to be deactivated, and then your osteoblasts are going to be activated, and they're going to fill in that space with new bone. And then you're back to having your normal bone. And this process is constantly going on every day of your life. So the turnover rate is very high. So about 1/5 of your skeleton is remade every year. So in 5 years, you essentially have a new skeleton. Now, if the osteoblast activity is greater than the osteoclast activity, so remember, osteoblasts are making the bone, osteoclasts are breaking down or resorbing the bone. So if you're making more bone than you're breaking down, we call this modeling. And this is the process by which your bones become stronger and more massive. So for example, exercise, if you put a lot of stresses on your bones through like lifting weights, running, doing various exercises, that will actually stimulate increased osteoblast activity, and it will make your bones denser and stronger. However, if the osteoclast activity outweighs the osteoblast activity, so now what we're saying is we're breaking bone down faster than we're building it up, the bones will weaken and become more brittle. And unfortunately, this is a normal part of aging. We'll talk about a little bit more in a bit, but this happens to everybody after the age of 30. So exercise can counteract it, but ideally, you want your activities of your osteoblast and osteoclast to be relatively equal. So as you break down the bone, you're rebuilding it. It does help if you rebuild a little bit more by increasing the osteoblast activity, but you definitely don't want your osteoclast activity to heavily outweigh your osteoblast activity. During this process, and since this process is constantly going on a daily basis, other minerals can be incorporated into the bone during this process, especially heavy metals and radioactive elements. The osteoblasts can mistake these for the calcium salts and put them in the bone instead. So this is kind of twofold. You can look in someone's bone like a skeleton and see what they've been exposed to over their lifetime. For example, like lead exposure, lead can get deposited into the bones. But it also has a downside. In the case of radiation, if you're exposed to radiation, those radioactive elements can be like basically cemented into your bones. And then this can have long-lasting health effects because later in your life, as your osteoclasts break that bone down to remodel it, it can release those radioactive elements and cause all sorts of problems all over again. And this is frequently an issue for people who've been exposed to radioactive fallout from like bombs or nuclear reactors that have, had issues, etc. I have a video to show you on remodeling. They are going to talk about how exercise and lack of activity can affect the remodeling process, but I want to go ahead and show you this video before we talk more depth about that.
The skeleton changes across the human lifespan. This is characterized predominantly by bone formation and growth throughout childhood, followed by a gradual loss of bone density that begins in early adulthood that can accelerate significantly in older adults. The density of bone is modulated by a group of cells including osteoclasts, which are multinucleated cells that resorb bone, and osteoblasts, which refill the resorption cavities created by osteoclasts. Osteoclasts anchor themselves to the surface of bone. This creates a microenvironment underneath the cell, which is referred to as the sealed zone. Within this zone, the osteoclasts create an acidic environment that dissolves the bone's mineral content. Once the mineral content of the bone has been dissolved, enzymes released from osteoclasts remove the remaining collagenous bone matrix to complete the process of resorption. Following resorption, osteoblasts move into the resorption space and start to produce and deposit organic matrix called osteoid. Osteoid, a substance made predominantly of collagen, forms a scaffold in which minerals including calcium and phosphate begin to crystallize. Some active osteoblasts become trapped within the matrix they secrete and thereby become osteocytes. Other osteoblasts will undergo apoptosis or will revert back to lining cells which cover the surface of bone. This cycle of bone resorption and formation is referred to as remodeling. There is also a process where bone formation by osteoblasts occur without prior bone resorption by osteoclasts. This results in an increase in bone mass and is referred to as bone modeling. Bone modeling promotes the growth of bones and is important for maintaining bone strength. Remodeling also plays an important role during bone growth by optimizing the growing structure. After the age of 30, most people experience a gradual loss in bone mass due to a relative decrease in the activity of osteoblasts compared with osteoclasts. However, there are many factors that impact the process of bone remodeling and influence the degree of bone loss we experience as we age. For example, medications such as glucocorticoids, which can promote osteoclast activity and also reduce bone formation. Proper nutrition and physical activity can help strengthen bone. It is also believed that osteocytes form a complex network in bone that can sense any increased workload on the bone and respond by triggering the differentiation and activity of osteoblasts to increase bone density. Conversely, when bone experiences reduced loading conditions, such as during long-term bed rest, resorption and remodeling increase to eliminate underloaded bone. Loss of bone mass reduces its strength and increases the risk of fracture. This highlights the importance of staying active, maintaining good nutrition throughout life, and being aware of personal risk factors associated with low bone density.
Now we'll talk about factors affecting bone growth, including exercise, nutrition, and hormones. So, stresses to bones during exercise actually cause electrical fields to be generated within the bone, and this is thought to be related to the osteocytes being able to sense how much stress is being put on a bone. But when the electrical fields are generated, osteoblasts are attracted and activated, and they work to increase bone density. So they move to that area and they start to produce more bone. This is how exercise can help keep your bones strong, because exercise is what causes those electrical fields to be generated. There is actually a medical application now that has come about from this discovery. So scientists have discovered that you can apply electricity or electric fields to bones to help them heal better and faster after a bone injury or a bone break. So heavily stressed bones, so someone who really exercises, does a lot of weightlifting, those bones will become thicker and stronger. And the areas where tendons attach, so remember a tendon connects a muscle to a bone, those will also increase in size. So that'll make the bumps and ridges and processes on the bone larger as well. So a heavier, thicker, stronger bone is going to be less likely to break. Unstressed bones, so someone who doesn't exercise, who's a couch potato, their bones actually will lose bone mass and can become thin and brittle. And this becomes a real big problem in bedridden patients, so patients who are confined to permanent bed rest. You have to worry about their bones becoming so thin and brittle that they can break just by standing up. So, nutrients in bones. So as expected, since bones are made up of a matrix that contains a lot of calcium phosphate, a regular dietary source of calcium and phosphate are important to maintain your bone. Making bone also requires small trace amounts of magnesium, fluoride, iron, and manganese. We call these trace minerals. But you definitely need a regular dietary source of especially calcium to maintain your bones. There's a hormone called calcitriol that we'll talk a little bit more about in another few minutes that is synthesized by the kidneys. And this is a hormone that's important for that calcium and phosphate to be absorbed in your digestive tract. So, for example, you know that drinking a glass of milk, for example, provides a lot of calcium. But if you don't have enough calcitriol, drinking that milk, the calcium won't get into your body because you have to have the calcitriol to absorb the calcium in your digestive tract to get it into your blood. Now, calcitriol is synthesized from cholecalciferol, which is another name for vitamin D. So this is an importance of having enough vitamin D in your diet because if you don't have enough vitamin D, you can't make calcitriol. And vitamin D comes from either vitamin supplements or the sun. So spending time in the sun, your body will make vitamin D. Vitamin C is also very important. Vitamin C is necessary for collagen synthesis. And remember, bone is a matrix of collagen fibers with calcium phosphate salts put around it. So you have to have that collagen. Scurvy is a condition caused by a deficiency in vitamin C. And with scurvy, you get a loss of bone mass and strength. One of the first things that happens is like your teeth will fall out because of the deterioration of the jawbone. Vitamin A is also necessary. It stimulates osteoblast activity, and this is particularly important for bone growth in children. So children who are deficient in vitamin A may not reach their full stature or grow as tall as they could. Vitamins K and B12 are also important for other bone proteins. So this is a list of all things that you want in a nice, well-rounded diet to maintain your bone strength. Hormones can also affect both bone growth. So growth hormone is made by the pituitary gland. You'll get more into the endocrine system next semester, but growth hormone stimulates protein synthesis and cell division and growth throughout the body, including your bones. Thyroxine stimulates cell metabolism and can also increase your osteoblast activity. Thyroxine is a thyroid hormone, and again, you'll get more into this in your endocrine system chapter next semester. Sex hormones, we're going to talk a little bit more about in this chapter. Estrogen and testosterone, these stimulate osteoblasts to produce bone faster than the cartilage growth at the epiphyseal plate. So if you remember when we talked about endochondral ossification, we said that once you reach puberty and you get your sex hormones, that causes the osteoblasts to outgrow those chondrocytes and all of the cartilage ends up disappearing and your bones will stop increasing in length. So the sex hormones are kind of like that final signal to say, okay, we're tall enough, let's seal these bones, get rid of the cartilage, this is going to be our final bone length. Estrogen can cause faster epiphyseal closure than testosterone. So estrogen actually can cause those osteoblasts to work a little faster. So what do you think this means for height differences between men and women? So if you think about it, estrogen causes the osteoblasts to move faster. That means they replace the cartilage faster. That means the bone stops growing in length sooner than in males. So that is why, on average, males tend to be taller than women, because their epiphyseal cartilage has longer to grow than women. And then calcitonin, made by the thyroid gland, and parathyroid hormone, made by the parathyroid gland, are also very important for maintaining bones. And they play a role particularly in calcium homeostasis, which we have a whole section on. And before we close out this section, we have a little part on abnormal bone development. So these are some conditions that can happen, for example, if certain hormones are out of whack when it comes to bone growth, or different mutations in your genes. So pituitary dwarfism is a type of dwarfism that's caused by an inadequate production of growth hormone in childhood. This results in all of the bones throughout the body being shorter and smaller than normal, because remember, growth hormone stimulates bone growth. We rarely see pituitary dwarfism in the developed world because it can be treated with synthetic growth hormone. So if a child is diagnosed and they're not showing the signs of normal growth and is determined to be pituitary dwarfism, they can be given growth hormone, which will allow them to reach their full height. The more common type of dwarfism, and the one that you will typically see, is achondroplasia, and this is also one of your clinical terms. This is a mutation that causes the slow growth of cartilage at the epiphyseal plate. So remember, your bones only get longer if the chondrocytes are growing cartilage at the same rate the osteoblasts are making bone. So if the cartilage slows down, then the osteoblasts are going to take over and the bones are going to be much, much shorter. And this is going to primarily happen in your long bones, which are your bones of your arms and legs and your fingers. So basically your upper arms, upper legs, lower arms, lower legs, your hands, your feet, your fingers, your toes. So people with achondroplasia end up with a normal sized torso, but they will have short arms and legs. And as I said, this is the most common form of dwarfism that you'll see. There is no cure for it because it is a genetic mutation. So the two types of dwarfism. Disproportionate dwarfism is where the body parts don't really match, right? So you've got like a normal sized torso, but you have short limbs. This is like achondroplasia. Whereas proportionate dwarfism is you're smaller than average all over, and this would be like with the pituitary dwarfism that we don't see much anymore. And you probably know a lot of actors or famous people with achondroplasia. One of them is the actor Peter Dinklage, who played in the Game of Thrones series. He has achondroplasia. So we looked at what happens if you have too little growth hormone before puberty. That causes pituitary dwarfism. If you have too much growth hormone before puberty, that causes gigantism. All of your bones increase in length. And so this results in super tall people. This would be like the people in the Guinness Book of World Records for being the tallest people. Acromegaly is when you overproduce growth hormone after puberty. So remember, after puberty, the bones can no longer get longer. They can only get wider and thicker. So in acromegaly, the bones will increase in width and thickness, and it produces a characteristic look where you've got like thick, broad hands and arms. The face takes on this really broad, thick appearance. And that's because all of the bones are getting thicker and broader because they can't get any longer at this point. And then Marfan syndrome is where you have a mutation that causes excessive cartilage formation at the epiphyseal plate. So this is like the opposite of achondroplasia. With achondroplasia, the cartilage grows slower, so the osteoblasts end up removing all of the cartilage while the bone's still very short. In this case, the cartilage keeps growing and it outpaces the osteoblast, so you end up with very, very long bones. So you have long limbs and digits, but unfortunately this syndrome also affects a lot of other types of connective tissue and can affect things such as the heart, which usually results in other types of health problems. And now we're going to talk about calcium homeostasis, which is a very important concept, and this is going to come back again next semester. So you really want to learn this and get this in your long-term memory. So this is one of those sections you might want to definitely watch more than once. So bone composition, you can think of bone as like a mineral reserve. So we already talked about it containing a lot of calcium and a lot of phosphate, but it also contains other things like potassium, sodium, magnesium, and carbonates. And so you can think of bone as a mineral reserve, but you can especially think of bone as a calcium reserve because bone contains 99% of the body's calcium. It also contains 99% of the body's phosphate, but the calcium regulation is very tightly controlled by the body because, as we're going to see in later chapters this semester, calcium can really affect the function of your muscle cells and your nerves. So calcium is the most abundant mineral in the human body. Your body typically contains anywhere from 2.2 to 4.4 pounds of calcium, and 99% of that is in your skeleton. So calcium, as I just alluded to, is super important. And here are some numbers you need to know. The normal calcium concentration in your body fluids, like your blood and your interstitial tissue, is 8.5 to 11 milligrams per deciliter. So remember those numbers, 8.5 to 11 milligrams per deciliter. And the reason this is so important, so this is the homeostatic level of calcium right here. If we increase the amount of calcium just by 30%, so just the 30% increase, your muscle cells won't work and your neurons won't work. So both muscle cells and neurons become unresponsive. That means your heart won't beat and your brain won't send signals. Conversely, just a 35% decrease in calcium concentrate in the blood and interstitial fluid, your neurons become hyperexcitable, and this means the neurons fire more electrical signals, and that leads to seizures and convulsions. And a 50% decrease in calcium will definitely cause death. So calcium homeostasis, keeping calcium between 8.5 and 11, is very important to the body. And in fact, if you're healthy and all of your systems are working correctly, the fluctuations on a day-to-day basis should never be greater or lesser than 10% away from the normal. So let's look at how your body maintains this homeostatic level of calcium. All right, so it does it with negative feedback. And remember, negative feedback means that we're going to act to reverse the change. So whatever the change was, we're going to do something to cause the opposite. So let's look at the first example. When calcium levels fall below normal, so if they go lower than 8.5 milligrams per deciliter, right? So they've decreased. So now we want to do negative feedback. We want to increase them. So how are we going to do that? The parathyroid gland is going to produce parathyroid hormone. And yes, you do need to know all this for the exam. Parathyroid hormone is going to stimulate osteoclasts. Remember, osteoclasts break down bone. So causing the osteoclast to work more means we are going to break down the bone. And if you break down bone, you're releasing the calcium from the bone and putting it into the blood. So remember, this all starts because our blood calcium levels fell. So we have to take calcium out of the bone and get it back into the blood. The kidney is also going to reabsorb calcium ions, and what that means, you'll get more about the kidney next semester, but what that means is keeping the calcium in the body instead of releasing it from the body through the urine. So the calcium is going to reabsorb calcium ions. That means there's going to be less calcium in the urine, and the kidney is going to release a hormone called calcitriol. The calcitriol is going to tell the intestines to absorb more calcium from your food and drink. So like if you drink a glass of water, you drink a glass of milk, now if you've got additional calcitriol, you're going to absorb more calcium from that glass of milk. So we're releasing calcium from bone, we're absorbing more calcium in the digestive tract, and we're keeping calcium in the body instead of releasing it in the urine. All of this together should be the opposite of what our stimulus was. So our result is our calcium levels increase back to normal. And keep in mind, we're talking about levels in the blood. All right, the other side of that is what happens when calcium levels rise above normal. So they get too high. They go above 11 milligrams per deciliter. Again, we want to counteract this and do the opposite. So we want to reduce calcium this time. So this time, the thyroid gland is going to release a hormone called calcitonin. And calcitonin is going to inhibit osteoclasts. So it's going to slow down those osteoclasts, which means less calcium is released from the bone. The osteoblasts are still working as normal, so they may even be putting some of the calcium back in the bone, but we're stopping the osteoclasts from releasing the calcium. The kidney this time is going to excrete calcium ions, and what that means is that they take them out of the blood and put them in your urine. So you're going to pee out more calcium in your urine. And then the kidney is going to slow the release of calcitriol. So it's going to release less calcitriol. Having less calcitriol means the intestines are going to absorb much less calcium. So now again, if you drink a glass of milk, this time you're not going to absorb as much calcium from that milk. It's just going to pass through your digestive tract and come out the other side. So with all of this, we're slowing release of calcium, we're slowing absorption of calcium, and we're getting rid of calcium in our urine. All of this together should decrease the calcium levels in the blood. So your body is bouncing back and forth between these two homeostatic mechanisms, the thyroid gland and calcitonin and the parathyroid and parathyroid hormone, to maintain that normal homeostatic level of 8.5 to 11 milligrams per deciliter. Very important. We'll come back next semester. In this section, we'll talk about bone fractures, the types, and how they heal. So a fracture is a term that we use to refer to either a crack or a break in a bone. So whenever you're talking about a broken bone, you're actually been talking about a bone fracture. Bone heals really well, so these fractures will repair themselves as long as you have a adequate blood supply and the components of the periosteum and endosteum survive, because that's where those osteogenic cells are that become new osteoblasts to help repair the bone. So there are several types of fractures. One of the major classifications is between open and closed. So an open fracture, which is also called a compound fracture, is where portions of the bone will actually project through the skin. So that's what makes it open. And a closed or simple fracture is when the break is completely internal, so there is no broken skin on the outside. There are other ways to classify fractures. For example, you can also classify them as non-displaced, which means the ends are still in position, as you can see from the third image over here, versus displaced, where the ends are out of alignment and need to be set back together. You can also categorize them as linear, which is shown in the second image. So the break is oriented to the long axis of the bone, versus transverse, where the break is perpendicular to the long axis of the bone. You can also categorize them as a complete break, which would be like the one over here on the right, and an incomplete break, which would be like this one here in the second example. So and there's other ways that you can categorize fractures too. These are just some of the major ones. So now let's talk about how fractures are repaired. So we're going to go through the stages of fracture repair. So whenever you break a bone, you're going to break blood vessels, right? So remember, we talked about how bone is heavily vascularized, so it has a whole lot of blood vessels. So it's impossible to break a bone without also breaking blood vessels. So when you break those blood vessels, you're going to get bleeding, and then you're going to get a blood clot that's going to clog up those arteries and stop the bleeding, and that's called a fracture hematoma. So a hematoma is another word for a clot. So this is a fracture hematoma, or a large blood clot that occurs in this area. The osteocytes around the fracture are going to die, because with those broken blood vessels, they're not going to get nutrients and oxygen, so they will die due to disruption in the blood supply. And so this area of dead bone, which is shown in this image, is sort of this darker ivory color compared to the lighter ivory down here at the bottom. This dead bone area is going to extend in both directions from where the break occurred. So the second step is that your cells in your endosteum and periosteum undergo rapid division. So remember, this is where you find your osteogenic cells. So they're going to start dividing and they're going to become osteoblasts. These cells are going to migrate to the fracture zone, so the area where the bone is broken, and they are going to differentiate into osteoblast, and some of them will actually differentiate into chondroblast, which are cells that make cartilage. And so they're going to basically make this little fix of a mix of cartilage and bone around the fracture site. And it's going to happen both on the outside and the inside. So the external callus is this enlarged collar of cartilage and bone that happen on the outside around the fracture site. And this helps to stabilize the outer edges. And then an internal callus is going to happen in the medullary cavity or within the spongy bone, and that's going to unite the inner edges, right? So we are basically creating areas of bone and cartilage on the outside and the inside. And those are called calluses. So basically think of this as a temporary bridge of cartilage and bone to stabilize either side of the fracture as the healing process continues. So now that we've got it stabilized, now we need to work to get it remade into proper bone shape. So osteoblasts are going to replace the cartilage with spongy bone. And then eventually you'll have these struts of spongy bone that will be uniting the two broken ends. Any dead bone that was around is going to get resorbed. Remember, resorption happens with osteoclasts, and then it's going to get replaced with the osteoblasts. And this is the stage where you usually have your cast taken off. So if you had a cast, this is when it would be taken off, because now the bone can withstand stresses again. It's all pretty much bone again. It's mostly spongy bone, but it's still bone and it can withstand some stress. And the last and final stage is over the next several months to years, the bone will continue to be remodeled. For a while, you will see the swollen external callus on the outside, but over time that will be remodeled and the bone will go back to look just like new. So the calluses will eventually recede and the bone is as good as new. And in fact, after this healing process, bone seems to be stronger than it was before. Because subsequent breaks in the bone usually occur at a different site. They don't usually occur at the same site twice. So this repair process actually can make the bone stronger in that location. Bones heal really well. So even if the broken ends aren't set back in place, the bone will still heal. So the reason that we go to the doctor and we get the bone set before they put a cast on is because otherwise the bone will just grow back however it's sitting. So on the right here is a femur from someone, probably this looks like a really old bone, so maybe before they had adequate medical care, and this femur had a break and it was not set, so the ends weren't realigned to each other, but it healed anyway. It just healed in a crooked shape. And you see this a lot in animals, dogs, cats, and wild animals too, especially wild animals because nobody takes them to the vet to get their broken bones set. But you can especially usually see it in cats and dogs who've broken their tail. Right, you can see that if it doesn't get set and put back in place, it'll heal, but it'll heal crooked, and sometimes you'll end up with like a bump in that area. So bone heals really well, whether or not you have it in the correct position that you want it when it starts to heal. I have one last video to show you, and this is a video about fracturing. And in this particular video, it's about fracturing due to bone loss, like with osteoporosis, which we're going to talk about next.
Our skeletons have evolved to be able to resist most fractures, but the extreme loading associated with trauma can create sufficient stresses and strains within bone tissue to cause fractures. Following the fracturing of bone, a blood clot forms between the two broken bones. Various inflammatory mediators are released at the site of damage, which recruits cells involved in the repair process. Following inflammation, connective tissue, such as cartilage, starts to form around the site of the fracture, forming a bridge between the ends of the broken bone. New blood vessels form by the process of angiogenesis to replace the vessels that were lost as a result of the fracture. Cells associated with these new blood vessels are involved in osteogenesis, or the formation of new bone tissue. Osteoblasts rapidly form woven bone, bridging the gap between the two pieces of broken bone. Once the fracture has been bridged and stabilized, remodeling occurs, in which osteoclasts, together with osteoblasts, remodel woven bone callus to normal lamellar bone, and to gradually restore the typical bone structure. While extreme loading can fracture any bone, fragility fractures can occur with less than extreme loading because of skeletal aging and structural decay. Vertebral collapse is often secondary to osteoporosis and is more prevalent in women. Loss of bone mass can be accelerated following the onset of the menopause, which can give rise to osteoporosis. This loss includes early and progressive declines in trabecular bone, which is more metabolically active, along with progressive declines in cortical bone. Cortical bone comprises 80% of skeletal mass. Cortical bone loss, caused primarily by increases in cortical porosity, may contribute to the increased risk of fracture. Another common fracture site is the hip, which is comprised of both cortical and trabecular bone. It is thought that cortical bone may play a greater role than trabecular bone in maintaining bone strength at the hip. Fractures of the hip have been associated with substantial morbidity, mortality, and healthcare costs. These events underscore the important role of cortical and trabecular bone in resisting fractures and highlight the importance of maintaining a lifestyle that helps to build and preserve bone strength. It is also important for older patients in particular to be aware of their personal risk of fracture and seek medical advice on how best to reduce that risk.
So the end of that video leads us nicely into our last section, which is on osteopenia and osteoporosis. So osteopenia is the term that we use for inadequate ossification, which leads to reduced bone mass. And this is the process that happens in everyone. So this begins in everyone starting between the ages of 30 and 40. This is when your osteoclast activity will be greater than your osteoblast activity. So osteoblast activity decreases, osteoclast activity stays the same, so you end up breaking down more bone than you rebuild. So women lose about 8% of their skeletal mass per decade, and men lose about 3% of their skeletal mass per decade. And again, osteopenia is the normal part of aging. So you can see down here normal bone, and then the osteopenic bone, where you're getting a little bit less bone. So the bone is not as thick and healthy and strong as it was when you were less than 30. Not all parts of the skeleton are equally affected. The areas that are more at risk are the epiphyses, or the ends of your long bones, and this can result in more fragile limbs, so more easily broken limbs. This also can affect your vertebrae, which leads to reduced height, and your jaws, which can lead to a loss of teeth as you age. So osteoporosis is the term that we use when the condition of bone loss has gotten so bad that it compromises normal function. So once it reaches the point that the bone cannot function normally, we now call it osteoporosis. So again, we've got normal bone, we've got osteopenia, which is the normal decline in bone that occurs with aging. And then if the osteopenia continues to the level where you've actually got compromised function, we call that osteoporosis. And with osteoporosis, fractures occur more easily. And then, of course, if you fracture a bone, that can result in a loss of mobility. So if you have to be bed rest, that will further weaken your bones, because remember, if you're not exercising or having activity and putting stresses on your bones, they will get weaker. This is particularly seen in hip fractures in the elderly. So an elderly person fractures their hip, they get confined to the bed, but being confined to the bed actually increases their bone loss throughout their body. So it's a vicious cycle. And osteoporosis involves reductions in both spongy and compact bone. Osteopenia usually just mainly affects the spongy bone. So we mentioned before about the sex hormones in bone. So we talked about how estrogen and testosterone help maintain normal bone. And one of the reasons that everyone has osteopenia as they age is because our release of sex hormones decline as we get older. Now in women, osteopenia will accelerate after menopause, because at menopause, women stop making estrogen. So once they stop making estrogen, osteopenia accelerates, and it's also why women have a higher risk for osteoporosis. Men will make testosterone for the entirety of their lives. Now, the levels of testosterone they make can decrease, so men can get osteoporosis as well, but the rates are usually higher in women because of the complete lack of estrogen. And that is the end of the bone chapter, or the end of the bone tissue chapter. The next 2 chapters are going to be on the different parts of the skeleton, and the 4th chapter in this unit will be on joints. So happy studying.